In this session, we'll be seeing when can we say two set of functional dependencies are actually equivalent. We'll be going to the definitions, like when can we say one functional dependency, a set of functional dependency say E is equivalent to another set of functional dependency F. When can we say so? Before that, let's see what does this equivalence mean using an example. Then we'll come back to this definition. Suppose you have two functional dependencies, F is there, that consists of two dependencies, A gives D and A gives C. And you have another functional dependency, G, which consists of A gives DC. Now, over here we need to see whether F and G are equivalent. Now, what does equivalency mean in this case is like, say, in G, we have A gives DC. So, can A gives DC be inferred from the set of dependencies in F? Say, in F we have got A gives D and A gives C. So, if we take the union of these two, that is one of the inference rules we had learned, it gives A gives DC. So, taking the union of these two, we get A gives DC. So, using the set of dependencies that is there in F, we get the dependency that is there in G. So, we can say F and G are equivalent. A gives DC can be obtained by applying union rule on functional dependencies in F. Similarly, functional dependencies in F can be obtained by, say, like G has A gives DC. So, if we decompose this into two, A gives D and A gives C, those are the dependencies in F. So, we can say F and G are equivalent. So, that's when we say two set of functional dependencies are equivalent. Now, let's go back to the definitions. First, we need to understand what we mean by a term cover. Then we will be seeing what we mean by equivalent. So, a set of functional dependencies F is said to cover another set of functional dependencies E. Here, E and F are the terms used. The example used F and G. Anything can be used for representation. So, a set of functional dependencies F is said to cover another set of functional dependencies E if every functional dependency in E is also there in F plus, that is closure of F. That is, there is two functional dependencies E and F, and on taking F closure means all the possible set of dependencies that can be inferred from F, and if that F closure consists of the dependencies that are there in E, we can say this if every dependency in E can be inferred from F, we say E is covered by F. That is, if F plus, that is F closure, consists of all the dependencies that is already there in E, we say that E is being covered by F. So, that term you need to understand what we mean by cover. Then, as we saw in the example, two set of functional dependencies E and F are equivalent if E closure equal to F closure. If we take the closure of the dependencies, if they give the same result, like in this, these two are equivalent. So, we say these two dependencies can be equivalent. So, we just try to understand two terms, cover and equivalence. Next, we need to understand a term like minimal cover. We will be getting problems from this topic. So, a minimal cover of a set of functional dependency E is a set of functional dependency F that satisfies the property that every dependency in E is in closure F plus. So, that was the definition of cover actually. So, if every dependency is in E is there in F plus, we say E is being covered by F. Now, in order to say F is the minimal cover, please try to concentrate on this. E and F are two set of dependencies. If F plus, that is closure of F, contains all dependencies that are there in E, we say F plus covers E, or E is being covered by F plus. Now, one additional term is coming, minimal cover. Now, when can we say F is the minimal cover of E? Till now we were just dealing with cover. Now we need to understand the term minimal cover. When can we say the set of functional dependencies F is said to be the minimal? For that, three conditions have to be satisfied. things would be more clear when we look example problem from this. So three things should be satisfied for that. The first one is every dependency in F has a single attribute in its RHS, that is right hand side. And like for example, consider x gives y. X gives y has just one attribute on the right hand side. X gives y z. If it is x gives y z, there are two attributes on the right hand side. So that if there is only one attribute, that is if it is the example is like x gives y, we say it is in canonical form. So the first step is that every dependency should be in canonical form. Don't confuse this canonical form with the canonical form or non-canonical form term in the fifth module under query optimization. Both have independent meanings in different contexts. So the first thing is there should be only a single attribute on the right hand side of each dependency. Second thing to be satisfied is there should be no extra attribute in the left hand side. We'll be seeing what this means. And there should not be any redundant functional dependency in the set. So if these three conditions are satisfied by the functional dependency set F, we say it is the minimal cover for E. So we'll try to understand this using a problem. Now consider the set of functional dependencies E is given. Like E has three dependencies. E is the set of functional dependency. E contains B gives A, D gives A, AB gives D. And we are asked to find the minimal cover of E. So we will be trying to understand how to obtain the minimal cover using these 3 points. So the set of dependencies are given. E contains these 3 dependencies. B gives A, D gives A, AB gives D. Now the first step was the RHS of all the dependencies should contain only a single attribute. So in this there are 3 dependencies. In all the 3 dependencies, the RHS consists of only one attribute. In this there is only A, in this there is only A, in this there is only D. So for all above dependencies, they are already in canonical form. We need not do anything. We can have a look at example where this step need to be applied in the next example. But in this example, we need not apply or do anything to satisfy that first condition, because all the right hand side of the dependencies are already in canonical form. All the dependencies are already in canonical form. Now what does the sorry. Now the second step says no extra attribute in LHS. So in this, which dependency can actually violate that condition? There should be no extra attribute in the left hand side. B gives A already has only one attribute in the left hand side. D gives A also already has only one attribute on the left hand side. AB gives D. So AB gives D has more than one attribute on the left hand side. So the question is, can we replace this AB gives D by, so in the second step, we need to determine if AB gives D has any redundant attribute on the left hand side. That is, can we replace AB gives D by B gives D or A gives D? How this came is, can we remove B from this? That is, can we write A gives D, or can we remove A from this and write B gives D? And still, it is equivalent. So how to find this out is, so this is a tricky part. Try to concentrate on this. So we need to see whether we can replace AB gives D by B gives D or A gives D. So for that purpose, we take the already existing dependency, say B gives A. So B gives A, if we augment means adding something on both the side. So if we augment with B on both the sides. So this was actually the second inference rule. So to understand this, you should be familiar with the 6 inference rules we had already discussed. That is the Armstrong axioms, that part. So since B gives A, and by augmenting B on both sides, we get BB gives AB, which is equivalent to writing B gives AB. Okay, B gives AB we can get from by augmenting B on both sides. However, what we are dealing with is AB gives D. So now we have B gives AB and AB gives D. So B gives AB, AB gives D. By transitive dependency, we can say B gives D, right? B gives AB, we have AB gives, how we got B gives AB? By augmenting B at both sides for B gives A. That is how we got BB gives AB, BB is B, so B gives AB. There is already the dependency AB gives D, which we are trying to deal on the left hand side. So B gives AB is there, AB gives D is there. So from that we can derive B gives D, right? So we were trying to see whether AB gives D can be replaced by A gives D or B gives D. So by augmenting a B over here and taking transitive dependency with this functional dependency, we get B gives D. So which means we can replace AB gives D by B gives D. So after the second stage, that is after second stage is no extra attribute should be there in the LHS. So by after removing that, we replace this by B gives D. Note this point, AB gives D can be replaced by either A gives D or B gives D only. One of this should come. So that in this case we obtain by taking applying the second inference rule on this, then taking transitive dependency between these two. That is how we reached the conclusion that we can replace it by B gives D. So after the second step, the set of dependencies now become B gives A, D gives A, and B gives D. That is, this third one is replaced by B gives D. So it has satisfied the second step. There is no extra attribute on the left hand side. Now the third step, there should not be any redundant functional dependency. So among the leftover functional dependencies, there should not be any redundancy. That is, mainly redundancy arises from transitive dependencies. So in the third step, you need to look whether any transitive dependency exists in this. As you can see, B gives D is there, D gives A is there. So from that we can derive B gives A, and that B gives A is there already there in the dependency set. I'll say once more, D gives A is there and B gives D is there. So from B gives D, D gives A, we can write B gives A. But that dependency is already listed. B gives A is already listed. So this B gives A is a redundant dependency and it can be removed. So B gives A can be removed and there exist these two. B gives D and D gives A exist after removing that. Why can it be removed? Because it can be obtained by transitive dependency of these two. So this is the minimal cover of E. E was actually this one. By following those three steps, we got E as this. So this is the minimal cover of E. That is, this satisfies all these three conditions. Now there is an algorithm to find this minimal cover. The algorithm as such has not been asked. If asked, you can also write it in sentence. You don't have to by heart this algorithm. I'll just explain how to explain if the algorithm for minimal cover is asked. So actually it is setting the set of dependencies E to be F, where F is the minimal cover. So in the minimal cover, all the dependencies exist. So what was the first step? Next step, it was ensuring that it is in canonical form. Canonical form means there is only one attribute on the RHS. So that is the first step. The second step, so this is equivalent to that first step. The second step is removing the redundant attributes on the LHS. So this is equivalent to the second step. And finally removing redundant functional dependencies. So this is equivalent to the third step. If possible, try to read and understand this, or you can try write it in your own words by describing these three steps with the example. Now, in order to see whether you understood how to find the minimal cover of a set of functional dependencies, here is a question for you. So what you can do is, I will just explain the question. After that, you can pause the video and try to solve this question on your own. The following next slide consists of the answer for this. So you can, after trying to solve it yourself, you can cross check with the answer in the next slide. So there's a relation like R gives ABC, and we need to find the minimal cover of the set of this dependency F. So the dependency given is A gives BC, B gives C, A gives B, AB gives C. This is a university question, and you need to find the minimal cover of F. So in this, actually that first step would be required. I will just give a clue for that. The rest of the things you may try to solve yourself. This is not in canonical form. A gives BC is not in canonical form because there are two attributes over here. This can be split into A gives B and B gives C. And you can see B gives C is already over here. So A gives B and A gives C. You can split this into two to make this in canonical form. The rest of the things can be done using the second step and third step. Try to do it on your own and then see the answer in the next slide. So I'm pausing over here and pause over here, try to solve this and then continue. So hope you tried on your own. Let's have a look at the problem. So the set of dependencies that were given is A gives BC, B gives C, A gives B, AB gives C, and we were asked to find the minimal cover for F. So the first step is making in canonical form. That is, there should be only a single attribute in the RHS. So in order for that, A gives BC is split into A gives B and A gives C. So as you can see, A gives B and A gives C. Okay, and the rest of the things, this A gives B is already there in this, so you need not write it two times. A gives B, A gives C, B gives C, AB gives C. So this is after the first step. In the second step, we need to remove the extra attribute in the LHS. So in this, the only possibility to violate that is this one, AB gives C. So we need to see, can we write AB gives C as A gives C and B gives C? Right, A gives C and B gives C. In this question, you can see that A gives C and B gives C is already there in the set of dependencies. In the previous question, it was more tricky. Actually, you had to derive it. In this, it is easier. A gives C and B gives C is already there in the set of dependencies. So you can actually remove this from this because this is a redundant one. So after this step, the set of dependencies becomes A gives B, A gives C, and B gives C. The third step is removing the redundant dependency, and redundant dependency usually arises from transitive dependency. We need to see whether any transitive dependency exists over here. So A gives C is there, B gives C is there. So actually B gives C, not this, A gives C, A gives C can be removed. Yes, A gives C can be removed from this. A gives B is there and B gives C is there. So from that, A gives B and B gives C, we can derive A gives C. So this A gives C can be derived from these two. So we can actually remove A gives C. The other two, that is A gives B and B gives C, would be left in F, and that is the minimal cover. And one mistake I have seen students making in this step is this A gives C is actually derived from these two. I have seen students actually remove these two and keep A gives C. It is not like that. A gives C can be derived from these two. So A gives C is removed and these two are kept. So A gives B and B gives C is the minimal cover of F. That is how we obtain the minimal cover for that particular functional dependency. Hope the problem is clear to you. Next, there is a standard procedure actually to find the key. Those of you had attempted the assignment, third assignment, would have tried this procedure on your own. Actually, this was the assignment question. We'll just discuss few things on this question, and that is how to find the key. We have already dealt with this, but we'll just spend some more time to discuss how to find the key. So the questions to find key would be like either it is related to normalization, or you would be asked to find the key. You'll be given a relation like R gives A, B, C, D. This A, B, C, D is actually the attributes. It can be meaningful attributes, but for exam, they might be using such common terms. R is the relation, A, B, C, D are the attributes, and set of functional dependencies are also given, and you may be asked to find the candidate keys. Now, when we do this, the finding the candidate key means finding the minimal key. In this, as you have already seen this problem, we know that AB plus, that is AB closure, gives us all the attributes. A, B, C, D, all the attributes in this relation. So we can say AB closure or AB to be a key. So something, or the closure of something that gives all the attributes, is taken as the key. So actually, if you take A, B, C, D, E closure and say it is a key, it gives all the attributes, but it is not like that. It should be the minimal set of attributes that leads us to all other attributes. So in this, how to find the closure, once more I can revise. AB closure means it contains AB, as it gives CD, it contains AB, CD, and using this, that is already in the closure there is ABC, so ABC gives E, so E is also added. So we get all the attributes using AB. Now how BC becomes the key is, now many of you may think I think for the assignment, for trying to find out the key, you may have started looking by the LHS of each functional dependency. So AB is a key. So now you might have thought, let's take ABC as another key. So ABC actually gives E and AB gives CD. ABC is also a key. Actually, ABC is a super key. Now, by removing A from this, by using only BC, also we can reach all the attributes. Let's see. BC means if you take just BC, BC is there, and from C, in BCC is there. So from C you get A. That is how A gets added. So now we have ABC. So with that AB you get CD, and using that ABC you get E. So using just BC also we can reach all the attributes. You get me? So now, so even though it is ABC on the left hand side, it is the minimal set that leads to all the attributes. Now if C alone led to all other attributes, we could have taken C as the key. But C alone does not lead us to all the attributes. C just gives A, and we are stuck over there. We cannot add any attributes after that. C gives A, and we require B to get this or this also. So we are stuck over there. So C alone does not give all attributes. That's why we didn't take C to be the key. And even in this, if A alone led to all other attributes, we could have taken A as the key. So the key is actually the minimal key, or the minimal closure of the minimal set that leads to all other attributes. That is said to be the key. So you have a simple algorithm stating how to find the key. Initially the key consists of all the attributes in the relation, that is k equal to r, and for each attribute in this relation we try removing one attribute at a time and try taking the closure, and it reaches a stage where we cannot remove any more attributes, and that k minus a plus contains all, if it contains all attributes, that is this closure contains, if it contains all the attributes in R, we can set that to be the key. So that is how key is found out. So I hope you got this. Like if you get such a question, don't just consider the left hand side of all the functional dependencies. If A alone or B alone or in this BC alone leads to all other attributes, that is going to be the candidate key. That's how you need to search for the key. It should be the minimal set. Hope you got that concept also. So this session we can end over here. Thank you.